Good afternoon. Today we will start a new topic, that is properties of pure substances. Now, a pure substance, it can remain at a particular phase or it can remain as a mixture of different phases. By phase, we means the state of the substance, like it can be solid, it can be in liquid phase, it can be either in vapor or in gas phase. There is a subtle difference between vapor and gas phase, which we will know when we will discuss further. Now, out of this, particularly when we will see the different engineering systems of our interest, we will find the working medium that could be either in the liquid phase or in the vapor phase or gas phase, or it could be a mixture of liquid and vapor phase. So, in engineering thermodynamics or the branch of engineering thermodynamics which we are studying, there we will be concerned for determining the properties, the thermodynamic properties of liquids, vapors and gases, and of course, the mixture of liquid and vapor. There could be some properties of a solid materials which are also thermodynamic properties, but we are not interested in that. Generally, metallurgists or physicists, they discuss regarding those properties. That is not within the discussion of the present course. Now, let us take one example. Let us say we take certain vapor in a piston cylinder arrangement, and the piston, it is loaded by a constant load like W, and inside this piston cylinder arrangement some vapor is there. There is a vapor. Now, and we are transferring heat to this vapor at a slow rate, so that at any instant the temperature of the vapor mass anywhere inside this piston cylinder arrangement is uniform and it is constant, but it is changing with time. That means, as we are giving or supplying more and more heat, the temperature of the vapor mass as a whole, it is changing, but it is not changing from point to point. Now, if we do this experiment and then if we try to measure its different properties, then what we will find? Obviously, if we transfer heat and there is expansion of this vapor mass, there will be change in volume. But we are applying a constant weight on the piston, so the pressure remains constant. So, it is a constant pressure process, the volume changes and there could be change in temperature. Now, if we note down the change of volume, then one can find out the change in volume with the application of heat. Similarly, one can think of a process in which we are plotting the change of volume. Either we can think of specific volume or we can think of total volume, and this side we have got pressure. So, we can think of the change of pressure and volume while the temperature is kept constant. So, the process will be something like this. let us say we are going for a cooling process. So, the process will be something like this. Here what we have done, we have kept the temperature constant. At this point, let us say we are coming to the saturated state of the vapor. So, we have started at any arbitrary pressure and volume and temperature of a vapor, then we are cooling it, that means extracting heat from the vapor mass, keeping the temperature constant, and then we are plotting the pressure and volume at different stages. So, at one stage we will reach the saturated vapor condition. After that, if we change the, or if we extract more heat, what we will find that temperature will remain constant and pressure will also remain constant till this saturated vapor completely gets converted into saturated liquid. So, at this point we are getting saturated liquid. After this, if we extract more heat, then we will find there is rise in pressure, but during this process there is very less change in volume. So, obviously here we are having a liquid state, and in the liquid state we know it is almost incompressible. So, the change in volume will be small. So, let us say this is at a temperature T1. We can repeat this process for another temperature. Let us say we repeat this process for another temperature and we will get something like this. So, that means we are getting basically three regions of the curve. In this region we are getting superheated vapor. In this region, this is the saturated vapor point. Here we are getting vapor liquid mixture. This is the saturated liquid point, and here we call it subcooled liquid. So, this is liquid, this is vapor, and in between we have a zone where mixture of liquid and vapor exists. Now, if we do this experiment for different temperatures, then we will have different points for saturated vapor. Similarly, we will have different point for saturated liquid. Now, if we combine all these points by some sort of a smooth curve, then you will get some sort of a dome like this. Let us say this is the line for which passes through points of all the saturated vapor, and this is the line which passes through all the points of saturated liquid. If they are extended, they will join at a particular point which is known as critical point. So, this point let me denote as C or critical point. Now, if somebody does the same experiment or same type of curves are plotted, then through the critical point one will get a curve like this. And beyond critical point, the nature of the curve will be something like this. So, let me write down. This side we are having liquid, which is denoted by L. Inside the dome we are having liquid plus vapor, and this side we are having vapor. So, L denotes liquid and V denotes vapor. These are these two, that means if we have the dome on the left hand side of the dome and on the right hand side of the dome, we have got single phase regions, while inside the dome we have got a two phase region or mixture of two phases. Now, for a pure substance, if it is in single phase, then if we know two independent thermodynamic properties, then any third property can be determined. All right. So, in this region or in the vapor region, if we know two independent thermodynamic properties, let us say if we know pressure and temperature, we can determine volume, we can determine enthalpy, we can determine entropy or any other properties for that matter. Similarly, in the liquid region, if say pressure and temperature are known, other thermodynamic properties can be determined. Well, in the two phase region, we need any three independent properties for determining another thermodynamic property. So, now we will see how to determine the thermodynamic properties and what are the important thermodynamic properties. So, mainly our working substance, that will be either in the gaseous phase or vapor phase, or it will be in the liquid phase, or it will be a mixture of liquid and vapor. And common working medium with which our engineering systems or engineering cycles run are like steam, it can be a refrigerant. So, basically for steam is used in number of engineering cycles, and it is a medium which is extensively used for the production of power. So, we will study the properties of pure substance with reference to properties of steam. So, for steam, the diagram which I have shown you is known as PV diagram for steam. This is the PV diagram. So, here these are constant temperature lines. So, this is a constant temperature heating line. Earlier I have shown a constant temperature cooling line. This point is known as critical point. This line is known as saturated vapor line, and this line is known as saturated liquid line. Similarly, one can have another thermodynamic plane for representing the pure substance. This is a TS plane or temperature entropy plane. In this temperature entropy plane, we can have constant pressure lines like this. So, this is a constant pressure line. So, we can call it P is equal to constant. Another line we can have, let us say this is P1 is constant, where P1 is greater than P. Here also we are having the critical point here at the top of the dome. C is the critical point. Then if I have these two lines, A to C or line AC, this is saturated liquid line and BC is saturated vapor line. Again, here we can see a dome type structure within which there is both liquid plus vapor. On the left hand side of the dome we have got liquid, and on the right hand side of the dome we have got vapor. At the critical point, one cannot make any demarcation between the liquid phase and the vapor phase, and at the top of the critical point we have got gaseous phase of the matter. So, this holds good for both PV diagram and for the TS diagram. That means, at the critical point we do not have any demarcation between liquid phase and vapor phase, and at the top of the above the critical point or at the top of the critical point we have got gaseous phase. So, as I have mentioned that for any pure substance, if it is in single phase, we need two independent properties for determining the third property or for determining any other thermodynamic property. Inside this dome we have got a mixture. Though it is a pure substance, here two different phases are existing together, liquid and vapor. So, here we need another information, one additional information for determining the property values. That information is known as quality or dryness fraction. Let us say we take a sample of a two phase mixture. So, sample of two phase mixture the mass of the sample is m. So, this is, as it is a mixture of two phases, so it is made up of partly with liquid and partly with vapor. Conventionally, liquid is expressed with a subscript f and vapor is denoted with a subscript g. So, m total, that will be mf plus mg. Now, quality or dryness fraction, which is denoted as x. So, x is mass of vapor divided by mass of the sample. So, in this case it will be mf by m, or it will be mf by mf plus mg. So, this quality or dryness fraction, that will be used as another property inside the two phase dome. So, if we go back to our earlier diagram, we can write at the saturated vapor line x is equal to 1, saturated liquid line x is equal to 0, and in between values of x, that will lie between these two lines. Or in other words, we will have different curves for different values of x inside the dome. So, these are constant x values or constant x lines. So, we can write x is equal to constant. Similar thing is there in this TS diagram. X is equal to 1, here x is equal to 0, and in between there are number of lines. Let us say this is one typical line where x is equal to constant. Though, as I have told at the beginning, we are not much concerned with the property of solid, but let us see the total scenario on a PT diagram, pressure temperature diagram. So, this is a PT plane for any thermodynamic substance. So, here transformation of phases can be denoted by lines like this. So, this side we will have solid, this is liquid, this is vapor, and this is gas. This is extended. So, if we give different names, this point is C and this is Tp. So, S denotes solid, L denotes liquid, V denotes vapor, and G denotes gas. C denotes critical point. Tp that denotes triple point. Now, this is a very important diagram. It shows depending on the values of pressure and temperature, what will be the phase of a particular substance, whether it will be in solid phase or it will be in liquid phase or it will be in vapor or gaseous phase. This line indicates transformation between solid and liquid. So, this line it indicates either melting process or solidification process. This line it indicates transformation between solid and vapor. So, this is indicative of sublimation and desublimation process. And this line it indicates transformation between liquid and vapor. So, it is boiling and condensation. And here we can see the critical point beyond which or at which there is no physical demarcation between the liquid phase and the vapor phase. Now, if we compare between this PV diagram and the PT diagram of a substance where all the three phases are shown, what happens? This is the saturated liquid line and this is the saturated vapor line. These two lines are coincident in this line where there is a transformation between vapor and liquid phase. In between there is a point which is known as triple point. It is a very important one, this point, and at this pressure and temperature all the three phases can coexist. So these lines shows the coexistence of two phases, but this point it shows coexistence of three phases. All the three phases can coexist at trippy point. So this is for the general information, but for for the branch of engineering thermodynamics in which we are interested in this line only, where transformation between vapor phase and liquid phase is taking place. So let us recapitulate once again what we have learnt so far, and then we will go for determination of different properties. What we have seen, that a pure substance, it can remain in different phases like solid, liquid and gas or vapor. As far as engineering thermodynamics is concerned, we are interested in liquid phase and vapor phase, and sometimes in gaseous phase. So in a pure substance, when there is transformation between liquid to vapor phase and vapor to liquid phase, in those processes we are interested, and those processes can be expressed on different thermodynamic plane. So two thermodynamic planes I have shown, one is a PV plane and another is a TS plane. So in all these planes we can see that there are three regions. One is a liquid region, another is a mixture of vapor and liquid region, and third one is the vapor region. And the liquid and vapor region, the mixture of liquid and vapor region, this is bounded by two lines in any diagram like this. On one side we have got saturated liquid line, on the other side we have got saturated vapor line. This saturated liquid line and saturated vapor line, they intersect at one point which is known as critical point. At critical point there is no demarcation between liquid and vapor, and above critical point we have got gaseous phase. So these are the important thing, and there is another important information which I have provided, that inside the two phase region we need another property for determining the any thermodynamic property of the mixture, and that property which we take generally is dryness fraction or quality. By definition, this is the ratio of the mass of vapor divided by the total mass. Now let me draw the thermodynamic plane which we generally use for discussing the change between the liquid phase and vapor phase. One is a PV plane, as I have shown. This is the PV plane. Another is a TS plane. The third one is HS plane. So HS plane looks like this. So in the HS plane also we have got the critical point. This is critical point C, and of course you will have different values of x like this. So this is x is equal to constant, and this line is your saturated vapor line. This HS diagram, where enthalpy and entropy they are taken as the coordinate, it has got another name that is known as Mollier diagram, or sometimes it is called Mollier chart. This diagram is very useful in solving problems because directly one can get the enthalpy values and changes in entropy in different processes from this chart. One can read directly. And as in different steady state, steady flow processes, changes of enthalpy is a very important quantity and it has to be computed number of times. So, this Mollier chart is very handy in calculating problems and representing different thermodynamic cycles. Other planes are also possible, like in refrigeration cycle we can use a different thermodynamic plane, but those we will discuss later on. So, mainly for steam properties or for the processes involving steam, we use to represent the process either a PV diagram or a TS diagram or an HS diagram. Now, which are the properties we are interested in? Let us say we will be interested in the specific volume. So, what is the specific volume? If we think of any thermodynamic plane, let us say we are interested in the TS plane, and in this TS plane we want to represent a process. So, the process the endpoints of the process that can be anywhere, either it can be in the liquid region or it can be in the two phase region or it can be in the vapor region. Accordingly, we have to determine the properties in those regions. Let us say we are interested in one property which is specific volume. V. So, if it is in the superheated vapor region, then we can determine it knowing other two properties like pressure and temperature. Similarly, if it is in the liquid region, we can determine it knowing two properties, two independent properties. Let us say again we take pressure and temperature. These two properties are easily measurable properties. So, from there we can determine what is the specific volume. But inside the two phase dome, what should we do? We can proceed like this. The mass balance if we make, so M sample, that could be M liquid plus M vapor. V sample, total volume of the sample, that could be V liquid plus V vapor. Then one can write M into V, that is, what is this quantity? This quantity is the specific volume multiplied by mass, that means it will give the total volume. So, that could be written as MF into VF plus mg into Vg, and then we can divide both sides by m. So, it will be mf by m into Vf plus mg by m into Vg. So, basically we are getting the specific volume of the mixture is equal to mf by m multiplied by Vf plus mg by m multiplied by Vg. By definition, the the term on the first term in this particular quantity is the dryness fraction or X. Similarly, here we can get what is MF? M minus MV Mg, that is your MF divided by M into Vf plus Mg by M into Vg. So, this will be 1 minus X into Vf plus X into Vg. One can simplify it slightly. So, one can write Vf plus X Vg minus Vf. This one can write. So, here either of these two expressions can be used for denoting the specific volume of the mixture. Either the first expression or the second expression can be used for determining or denoting the specific volume of the mixture. So, what do we need for determining the specific volume of the mixture? We need the specific volume of the fluid and we need the specific volume of the gas or vapor, and at the same time we need the mass fraction of any of this component, or we need the quality or dryness fraction. If we go back to this diagram, let us say this is a constant pressure line. This is a constant pressure line and we are interested at this pressure let us say this is a constant dryness fraction line. Let us say this dryness fraction is 0.75. So, we are interested at P bar and at dryness fraction is equal to 0.75 to determine what is the specific volume of the mixture. So, what we have to determine? First we have to know what is Vf. So, that Vf corresponds to this value of the saturated liquid. We have to know Vg. Vg corresponds to the specific volume of the saturated vapor at P bar, and already it is specified that we have to determine it at X is equal to 0.75. So, we know the magnitude of this quantity Vf here, we know the value of Vg here, we know the value of X here. So, that can be plugged in this equation and ultimately we can find out the specific volume of the mixture. This holds good for any other property, like if we want to determine enthalpy, we can use similar type of additive formula. If we are interested to determine entropy, we can use similar type of expression. Sometimes instead of using Vg minus Vf, their difference is used, and then this expression is like this: V is equal to Vf plus x Vfg. That means this is the difference between Vg and Vf. So, this expression is also used in some of the occasions. Now, for determining the steam properties, we use steam table. This is a very useful tool. Steam table is a very useful tool for thermodynamic calculations, where steam is the working substance, or steam and water are the working substances. Now, steam table, there are different steam table available in market. We can use them, and only thing is that we need to know how to read the steam table. Steam table mainly it has got different parts. So, in the first part of the steam table, we will see that property of saturated steam or saturated vapor and saturated liquid, that will be given in the first part. So, property of saturated liquid. That will be given in the first part of the steam table. Saturated liquid and vapor. So, basically we can say that property of saturated fluid, that will be given in the first part of the steam table. Which are the properties that will be given? Here properties like pressure, temperature, specific volume, enthalpy and entropy will be given. Now, steam table, either it can be the properties are tabulated based on pressure, or it can be tabulated based on temperature. So, in most of the steam table, both we will find that tables based on pressure or pressure based table, and table based on temperature or temperature based table, both we can find in most of the steam table. So, if there is a table which is temperature based, so there property values will be given at regular intervals of temperature, and temperature in the steam table, that denotes the saturation temperature. If we give the saturation temperature from any of these diagram, either this diagram, either the PV diagram or the TS diagram. So, in this PV diagram I have shown a constant temperature curve. Let us say T is constant here for this green curve. So, if T is constant within this two phase zone, for this portion of the curve, P is also constant. That means, what I mean to say, if I specify the temperature and call it the saturation temperature, automatically the saturation pressure becomes fixed. So, once I give the temperature value, then the pressure value is also fixed, because I am determining the property or at the saturated state, either for the saturated vapor or for the saturated liquid. So, similar thing in this curve also, this is P is equal to constant, but we can see in the two phase zone also T is constant. So, same thing holds good. That means, if I give if I specify the pressure, temperature remains constant, because we are determining properties at saturated condition. So, a pressure based table or a temperature based table, let us think of a temperature based table. A temperature based table will be something like this. We will have temperature, then we will have pressure, then we can have Vf, that is the specific volume of the liquid. We can have Vg, we can have Vfg also in some tables. Then we can have Hf, Hg, Hfg, Sf and Sg. So, this is temperature, this is pressure, this is specific volume for saturated liquid, this is specific volume for saturated vapor, this is the difference of specific volumes for saturated vapor and liquid, this is enthalpy of the liquid at saturated condition, this is enthalpy of the vapor at saturated condition, and it is the difference between these two quantities. Then this is the enthalpy of entropy of the saturated liquid, and this is the entropy of the saturated vapor. Now, the units which are used, we use SI unit. So, one can have degree Celsius here, pressure we can have kilopascal. All these three quantities, they can have a unit of meter cube per kg specific volume. All these three quantities, three enthalpies, they can have a unit of kilojoule per kg. This is specific quantity per unit mass, and these two entropies, again it will have kilojoule per kg Kelvin. So, these are the units which will be used in the steam table. Here, this is interesting to note in this context, that we are getting or determining the quantity HFG. This quantity HFG has got a physical meaning. It is also, from the physics point of view, this is one quantity which is of interest. What is this quantity? HF is the enthalpy of saturated liquid. Hg is the enthalpy of saturated vapor. So, HFG is basically Hg minus Hf. That means, this is the difference between the enthalpy of the saturated vapor and the saturated liquid, or in other words, we can write Hf plus Hfg, that is equal to Hg. So, now here this is the enthalpy of the saturated liquid. It needs some more enthalpy to get converted into saturated vapor at the same pressure and temperature. So, what is this quantity? This quantity is the latent heat of vaporization. So either it is latent heat of vaporization or latent heat of condensation, whichever process we may consider. So HFG has got a physical meaning that it is the latent heat of vaporization. So these are the quantities which we can read directly from the steam table, and this is a pressure based tabulation for the steam table. Similarly, one can have a temperature based tabulation. Sorry, this is a temperature based tabulation of the steam table. Similarly, one can have a pressure based tabulation for the steam table. In that case, what will happen? We will have P to start with, and property values will be tabulated at regular intervals of P, and then it will be followed by T. So corresponding to this pressure, the saturation temperature will be tabulated here. So what is the difference between these two tables? Here we will see a regular interval of temperature, but pressure intervals will not be regular. Whereas in the second case, here we will have a regular interval of pressure, and corresponding saturation temperatures will be tabulated in the next column, but the temperature intervals may not be regular. It will not be, in fact, it will not be regular. So that is the only difference between these two tabulation of steam table. Next, what we will do, I will take some example and explain how the data are tabulated and what can we do with the help of this data. So we will continue in our next class.